In previous videos, I have shown you how to apply the method of the first algebra of magnitudes to what is commonly known as the rule of three, including the simple, direct, and inverse cases, as well as the compound, direct, inverse, and mixed cases. And in all of them, what I have told you is that you need to calculate the equality between resources and work, on one hand for the statement, and on the other for the question. Now, the question I want to address in this video is why resources are equal to work, according to the first algebra of magnitudes. I am leaving a link in the description to each of the articles by the author of the First Algebra of Magnitudes and Dysmetry, which I will explain to you in a moment, so you can take a look if you want. They are open access, meaning they are free. And these are very interesting articles, in which he investigates the First Algebra of Magnitudes and Dysmetry in relation with such important topics as Einstein's theory of relativity. To do this, I must emphasize what the concept of the dyad or of measurement is. It is composed of two elements, a number and the magnitude or dimensional element. For example, here we have three dyads, 2 workers, 3 days, and a trench of 10 meters. Let's look at the case of the dyad of 2 workers. This dyad is made up of the numerical element, which is 2, and the dimensional element or magnitude, which is worker, which is what gives physical meaning to that dyad. The 2, which is the numerical element, we know exactly what it means, that we have 2 units of those workers. Now the question is, according to the first algebra of magnitudes, how do we operate with that magnitude of workers? In a previous video, I already mentioned this by referring to geometric algebra, or the algebra of magnitudes. That is, we are going to operate with these magnitudes from a geometric point of view. And for that, what are we going to do? We have the magnitude workers within this dyad. We are going to define a segment of a certain length that represents a worker, so that this segment I'm drawing on the board is a worker. But we have 2 workers, so we add this segment twice. In other words, it's an addition. Why? Because it's the same magnitude. This is what is called homogeneous dyads. Why? Because the first segment is a worker, and the second segment is a worker. And what we are doing is adding them, and since these are homogeneous dyads, or of the same magnitude, it's a geometric sum, which we symbolize with this symbol to differentiate it from arithmetic addition. And this is what results in 2 workers. And those 2 workers are the final segment, which is the sum of the 2 initial segments. In the case of 3 days, exactly the same thing happens. The number 3 is the arithmetic or abstract number that represents the number of units we have of this segment. And days is another segment of equal or different length. It doesn't matter here whether it's the same or a different length. In fact, so you don't get confused, we're going to make them the same length here. And this new segment is day. But we have 3 of these segments, so we add these 3 segments together to get a final larger one, which is the result of adding segment day plus segment day plus segment day, which ultimately gives us 3 days. Once again, we've performed the consecutive addition of this day segment, since we're dealing with the same magnitude or dimensional element. In other words, these are homogeneous dyads. Now then, what happens next? On one hand, we have 2 workers, which is the first dyad we've defined, and on the other hand, we have 3 days, which is the second dyad we've defined. And it turns out that workers is one magnitude, and days is another magnitude. In other words, they are no longer homogeneous, they are different, they are heterogeneous. And the geometric combination of these 2 segments gives rise to the work, which is the 10-meter trench. Therefore, we can no longer add the worker segments to the day segments in such a way that a third segment of even greater demi-dimension results. Instead, what we have to do is algebraic multiplication, which the first algebra of magnitudes has symbolized with the asterisk. Now then, graphically, what does this geometric multiplication consist of? We take the 2 worker segments, that is, we take the 2 workers we have, multiply them by the 3 day segments we have. In other words, we multiply by 3 days, and as a result, we obtain an area. And what is the result of this area? Precisely the work we aim to achieve, the 10-meter trench. And that is precisely why available resources will always be equal to the amount of work. These particular problems are very much simplified compared to real-life scenarios, okay? But moving on to real life, let's analyze a specific case. Let's analyze, for example, the measurement of speed. Speed traditionally, according to the International System of Units, is defined as kilometers per hour to the inverse. Or in other words, kilometers per hour to the power of -1. Alright, but what is the reasoning according to the first algebra of magnitudes for the magnitude of speed? Well, let's analyze it step by step. In real life, what are these measurements related to? A kilometer is a measure of distance, that is, distance is measured in kilometers, in this case. Okay? In real life, in nature, we all know what a meter is. A meter can be said to be about this distance, approximately. We see it everywhere. We define a starting point and an end point, and we get the meter. If we want 1,000 meters or 1 kilometer, well, that would be 1,000 of these segments in a row, added together as we've seen before. Perfect, up to this point, no problems. An hour, we all know what an hour is. The unit hour represents a specific period of time during the day or night, and between that starting point and that ending point in time, we have an hour. But what is an hour to the inverse? Or what is a meter to the inverse? Can we see the inverse meter or the inverse hour in nature? Can we perceive them? We cannot perceive them. That said, let's continue. Apart from the instance, we have time, which we measure in this case in hours, and finally speed. How do we measure it? That is in this case our unknown. Alright? We want to establish what the unit of speed is. How is it measured? What is its magnitude? What is the dimensional element of speed? Alright, let's think. We have distance, time, and speed. Of these three-dimensional elements, which are the resources and which is the work? Well, look. If we are moving at a certain speed for a certain amount of time, what do we get? A final distance traveled. So, what are the resources? Time and speed. And that will be equal to the distance. So between time and speed, if we combine them through a geometric multiplication, because they are indeed two-dimensional elements or two completely heterogeneous magnitudes, they're not of the same type, well, it turns out that we get distance. Graphically, what would we have? Well, we would have the time segment multiplied by the speed segment, and that gives us the area representing distance or work. But here, what we want to calculate is the unit in which we are going to measure speed. It's very simple. We have speed, which is equal to distance divided by time. That is, we've measured distance in kilometers and time in hours, kilometers per hour. This doesn't mean that the inverse of an hour exists, okay? What this means is that within this dyadic relationship between time, speed, and distance, the hour can indeed act as a divisor. Of what? Of distance, the kilometer. So that's the unit in which we're going to express speed. Where am I going with this? We have just reasoned step by step, according to the First Algebra of Magnitudes, what the unit of measurement for speed is, which is kilometer per hour, but within the geometric context or within the context of magnitudes of the Algebra of Magnitudes. However, the International System of Units states that speed is measured in kilometers per hour to the power of -1. That is to say, that the inverse of the magnitude hour exists. But that's not true, okay? Hour can be a divisor within this dyadic relationship, as I have explained to you, but it cannot. There is no such thing as the inverse of hour. In other words, when the International System of Units refers to a magnitude to the power of -1 or -2, as in the case of acceleration and seconds to the power of -2, it is falling into the trap of arithmetization. Why? Because it adopts a very formal language that mixes magnitudes with their derived units, but does not justify or explain their physical meaning. That is, it relies exclusively on numbers and forgets about the magnitudes. In trying to explain, in trying to clarify the definition of each magnitude, it ends up forgetting to justify them with magnitudes and relies exclusively on numbers. Be that as it may, the First Algebra of Magnitudes is the only one that has been able to explain and solve the problem of the arithmetization of physics since Newton. In other words, we have been falling into this problem of arithmetization for centuries. And such is the development, verification, and demonstrations carried out by the First Algebra of Magnitudes, that from there it has led to the dismetry of magnitudes. That is, in the examples I have given, we have defined the worker magnitude with a segment always of the same dimension on one hand, and the day magnitude as a segment always of the same dimension on the other hand. However, what if it turns out that the same magnitude measures differently depending on the context? For example, does a meter on Earth measure the same as in a black hole? That is what dismetry is about. And thanks to dismetry, answers are given to huge questions such as quantum theory, the number pi, or Einstein's theory of relativity. As I mentioned at the beginning, I'm leaving a link in the description to each of this author's research articles, which are also open access.